All right, so let's return or follow up on this permutations with repetition. Repetition has more than one t-net. Okay, and so we were working on this example. I'm going to bring it back. Banana. Sorry, I know the question is really how many words can you make with letters in banana. And so what we're doing is thinking about how many ways to scramble these. And so let's just recall from the last video. You can do, for instance, you could do, of the 6 blanks, you could choose where the A's go. So 6, choose 3. And then you could choose of the 3 remaining blanks, 2 of them to put the N's, and then you can place the B. Right, and you have the other variations, right, depending on which letter set you want to place first, second, and third. Right, so that's just the outcome if you do the A's, then the N's, and then the B's. And remember, the book's notation for this process is 6, semicolon, 3, 2, 1. Okay, so another way of doing this is to view this in terms of something called a multi-selection. Right, so we have done something called n choose k already. Right, and it's n factorial over k factorial and then minus k factorial. Okay, now this particular selection counter, if you will, n choose k is a selection counter. It is, on the face of it, counting just one group, k, but intrinsically you can't just have one group. There's actually also another group, and that's the leftover group, the n minus k's. Right, so truly you're actually making 2 groups when you do this, and although notationally it's not really used because it's too much work for what it means, would it be acceptable to write this? N choose k comma n minus k. Alright, now like I said, I mean this is just not done because it's not worth the time and effort, but for where we're going, this is okay. Now for multi-selections, there's a way of selecting multiple groups. This one chooses 2 groups. You could choose a bunch more. So K1, K2, K3, all the way up into however many groups you have. I don't know, so let me give a letter M. You have M groups, right? Maybe you have 17 groups. In this case, we'll have 3 groups. What does this mean? Well, this means you have n factorial over k1 factorial, k2 factorial, and so on. And this is because permutation within the group, the k1 group, the k2 group, doesn't matter. All right, or depends on how you look at it, right? So in this case, that statement makes a lot more sense, right? Permutation within the A's doesn't matter. Now, there's other applications where that language might not be appropriate, but so there's that. Now, there's something incredibly important about this when you start writing out this multi-selection stuff, and that it is very important once you go beyond one group, which is intrinsically 2 groups. Once you go beyond that, these bottom numbers need to add up to be n. Otherwise, you've left some stuff out, and there's an extra group hanging out that you need to include in this calculation. So, while we could deal with it, I would say it'd be considered bad manners to not have your numbers add up to n. Okay, if they don't, then intrinsically there's going to be an extra factorial for that leftover. Exactly like this, right? When we do n choose k, k does not add up to be n typically, and so there's a leftover group. Okay, but in this one we generally just put all the groups. That way it's crystal clear about how that breaks down. All right, so for this one, what's going on? Well, what I kind of want to show is, first of all, let's calculate this. So 6 choose 3, 3 choose 2, 1 choose 1. And I'm going to start by writing out what that is. So 6 choose 3 is 6 factorial. There's a 3 factorial. And then 6 minus 3 factorial is also 3 factorial. Alright, next one, 3 factorial. Then there is a 2 factorial and a 1 factorial, right? 3 minus 2 is 1. And then lastly, there's 1 factorial. Choose 1 factorial, and then 1 minus 1 is 0 factorial. Okay, remember, 0 factorial is 1. There's one way to order 0 objects. Alright, so what's going to happen is that the leftover group, in this case, right, when we chose 3 blanks, there are 3 blanks left. That's always going to appear as this n minus k bit here. It's always going to cancel with the next top number. Right, and when we chose 2 of the 3 blanks, there is 1 blank remaining, and that's going to cancel with the next one. Alright, so what happened here is we ended up with, and there's always going to be a 0 factorial left for 0 leftovers, so let me go and cross that off. So what we ended up with here is 6 factorial, 3 factorial, 2 factorial, 1 factorial, and so what I'm trying to connect this to is it's equivalent to doing 6, choose 3, 2, 1, and you can reorder these, right? Just like you can reorder how you want to place the letter groups, right? If you do n's first or b's first, and then if we do second and so on. Okay, so you can reorder these numbers to be 2, 3, 1, or 1, 2, 3, or 1, 3, 2. It's all the same thing though, right? Because multiplication is commutative. All right, but what's nice here is this kind of completes this process in basically one step, depending on how you look at it, but I think it completes it in one step, right? We're selecting 3 blanks, 2 blanks, and 1 blank. A's, in this case, A's, N's, and B's, right? So this is called a multi-selection, and it does not seem to share the language of permutation with this because the viewpoint of this is selecting from the blanks, all right? And that is actually how we went and worked on this problem anyway, whereas this particular look has that permutation field as you're permuting objects. I do not actually use this notation and never really have been a fan of it. That doesn't mean that it's incorrect notation and it's not usable, so feel free to use it if you prefer it over this. For instance, in email, this is quite handy because it sits on a line, right? You have these letters on your keyboard and you can make it fit on a single line. But I prefer this particular viewpoint of the problem as a multi-selection. All right. Now, what I want to do is we're going to start making connections to permutation through repetition with n choose k, which we've actually sort of done already. We're going to start building on tools to help count other problems that involve a lot of this sort of repetition as a wrinkle in the counting. All right, so I think that's most of what I wanted to say about this topic here. But keep in mind, when it comes down to actual practical problems of this sort, things are relatively straightforward, right? So if you were to ask to how many ways can you reorder the word banana, you could just answer one of these two, right? Very, very quick and easy to do. Typically, from your perspective as a student right now, reordering words with letters in it. If you had to do Mississippi, you'd easily do that, and so on. All right, so we'll see those in definitely examples later on. All right, by the next one, we're going to pick up permutation and repetition. We're going to work on just 2 letters in our word, but with repeats of each, and build from there. All right, see you next.